The first chapter of the course, Engineering Mathematics 1, is on further transcendental functions. A function is a relation used to identify the way a certain quantity depends on another quantity. This terminology was introduced by Leibniz in 1694. In 1718, Johann Bernoulli defined functions as an expression that consists of constants and variables. In your high school and pre-university, you must have learned about functions including exponential function, logarithmic function, and also trigonometric function. In this course, we will focus on the hyperbolic function and the inverse functions, including inverse trigonometric functions and inverse hyperbolic functions. These are the contents of this chapter. As I mentioned earlier, we will start with the hyperbolic functions, the definition and graphs, and the hyperbolic identities. Then we will discuss on the inverse functions, including inverse trigonometric functions and identities, inverse hyperbolic functions and identities, and the log form of the inverse hyperbolic functions. You may be wondering why we need to study about hyperbolic functions. Is it a new function? Well, the hyperbolic functions are not entirely new. They are simply common combinations of exponentials. We need to study them because of their usefulness in applications. For example, if you look at the photo, that is the Gateway Arch in St. Louis, United States. It is one of the most distinctive and recognizable architectural structures in the United States. Now, when you look at the arch, do you think that the arch is taller compared to its height? Most people think that it is taller, but this is the result of a common optical illusion. In fact, the arch has the same width as height. It is not a parabola. The shape corresponds to the graph of the hyperbolic cosine function, or called a catenary. Okay, so in this chapter, we will study on this function and other hyperbolic functions. Let us start with the definition of hyperbolic functions. The first one is the hyperbolic cosine. So we usually pronounce it as cosh x. It is defined to be exponent x plus exponent negative x divided by 2. So, here you can see that it is actually the combination of exponential functions. The second one is the hyperbolic sine, or we call it as shine. We pronounce it as shine. So, it is exponent x minus exponent negative x divided by 2. And for tangent hyperbolic x, we know that tangent hyperbolic x is equal to sine x. over cos x. So we know that sin x is equal to exponent x minus exponent negative x over 2, and cos x is exponent x plus exponent negative x over 2. Okay, so we will get exponent x minus exponent negative x over exponent x plus exponent negative x. Okay, and we can also simplify it to be exponent to x minus 1 over exponent to x plus 1. Hyperbolic secant is defined, okay, we know that secant is equal to 1 over cos. Okay, so secant x is equal to 1 over, so just now we know that cos is exponent x plus exponent negative x over 2. So this is equal to 2 over exponent x plus exponent negative x. So similarly, we have the cosecant, okay, which is 1 over sin. So we obtain it to be 2 over exponent x minus exponent negative x. And cotangent x is cos x over sin x, which is equal to exponent x plus exponent negative x divided by exponent x minus exponent negative x. So these are the definitions of the hyperbolic functions, which can be seen that it is related to exponential functions. Now let us take a look at the graphs of the hyperbolic function. So first, graph of sin x. So we know that sin x, the definition is equal to exponent x minus exponent negative x over 2. Okay, so y exponent x over 2 is, okay, so let's say we have here, let's say we have 1 over 2. So this is the graph y equal to exponent x over 2. And then if we have here, let's see here, negative 1 over 2. So we have the graph y equal to negative exponent x over 2. So the graph sin is exponent x minus exponent negative x. So you see here, this is 1 over 2. If you take at 0, x equal to 0, so this is my x, this is my fx, which is equal to sin x now. Oops, sorry. Okay, so if we take at x equal to 0, so exponent x over 2 is 1 over 2, and exponent negative exponent x over 2 is negative 1 over 2. So that's why we get the graph to be 0. So similarly with other parts. Okay, oops. So from the graph, we can see that sin 0. So when your x equal to 0, this is equal to 0. All right. So now we want to find the domain and the range of the graph. So the domain and the range of the graph is important in finding the inverse function later. Okay. So what is the domain? Or we denote it as df of the function sin x. So your f now is sin x. So fx equal to sin x. So you can see that your value of x can be all real numbers. So the domain is all real numbers. Meanwhile, the range, we denote it as RF. Okay, so you can see that your graph at the fx at vertical axis fx, it goes to negative infinity to infinity. So the range is also the real number, all real number. And this graph is symmetrical about origin. Okay, symmetrical about origin. So that means that sine negative x is equal to negative sine x. Okay. And we also can see that it is a one-to-one function. So what does it mean that by one-to-one? That means that if you take a value, of fx, let's say here, okay, it will only map you to one value of x. Okay, so if you have, let's say, f1 is equal to f1x is equal to fx1 is equal to fx2, that means that your x1 and x2 are equal. So that means that if you take any value of x, you only will get one value of x. Okay, so it is one-to-one function. And it is increasing. All right. Now, let's take a look at the graph of cosine. Okay, so let us recall cosine x is equal to exponent x plus exponent negative x over 2. Okay, so exponent x over 2, so this is, let's say I have here 1 over 2. So exponent x over 2, we will have this graph. Oh, sorry. So this is fx equal to exponent x over 2. Meanwhile, if I have exponent negative x over 2, so I will have the graph to be, so it will still cross at x equal, fx equal to 1 over 2. So this one is fx equal to exponent negative x over 2. So you see, when your x equal to 0, you have your f equal to 1 over 2. So this is your fx. This is your x. Okay, 1 over 2 plus 1 over 2, you get here 1. Okay, so same with other points. Okay, so from the graph, you can see that cos 0 is equal to 1. Okay, so what is the domain? Okay, so the domain, it can be the whole real number. So domain df is the whole real number, because you see the value of x can be from negative infinity to infinity. But in this case, the range, okay, for just now, we see for sine x, we can see that the range is from negative infinity to infinity, because the value of your fx, okay, the vertical, it comes from, it can goes up to negative infinity, and it can go down to negative infinity, it can go up to infinity. But for the cos, its range is not real number, because we have the value of cos x to be limited, okay, to be bounded by 1. Okay, so the range Rf is equal to any value of y. Okay, so let's say y equal to fx, such that y is greater or equal to 1. And it can be up to positive value. We can also write it as 1 to infinity. Okay, because above it can goes up to infinity, but below the graph it is bounded by 1. Okay, and you can see that it is symmetrical about y-axis. It is symmetrical about y-axis. So we know that cosh of negative x. So if you take negative x, for example, let me take here. Okay, so negative x. Maybe I take here. It will be similar value. So cosh negative x is equal to cosh x. So is it 1 to 1? It is not 1 to 1 because let's say I take this value. If I take this value here, you can see that I have 2 value of x. Or maybe I just take, for example, 4. My fx equal to 4. If I take my fx equal to 4, okay, so I have 2 values of x. Okay, 2 values of x. Okay, so it is not 1 to 1. Not 1 to 1. Okay? Alright, so this is the graph for tangent hyperbolic x. Okay, we know that tangent hyperbolic x is equal to sine x over cos x. Okay. Alright, so this is the graph, how we get it, similar as how we obtain the graph of sine and cos. Okay, but for this graph of tangent hyperbolic x, we can see that it has asymptotes. Okay, so maybe I take orange. Okay, so you see that it approached 1 but never reached 1. Okay, and also negative 1 and also negative 1. So this line, these two lines, we call them as asymptotes. Asymptotes, where y is equal to plus minus 1. Okay, now let's take a look at the graph and see what we can get. We know that tangent hyperbolic of 0 is equal to 0. Alright, now the domain df, okay, so you see your x can be from negative infinity to infinity. So it will be real number. And then the range, okay, so the range is limited at the asymptote. So negative 1 and 1. So your range f is y such that y is between negative 1 and 1. But does not include 1. It will not approach negative, it will not achieve negative 1 and 1. So y is from between negative 1 and 1. Okay, if you see for cos just now, it does include 1, but for tangent hyperbolic, it does not include 1. Okay, so you can see that it is symmetrical about origin. Okay, so therefore your tangent hyperbolic of negative x is equal to negative tangent hyperbolic x. Okay, so we have horizontal asymptotes, which is equal to y equal to plus and minus 1. So your y is equal to fx. Okay. The net graph is secant x, which is equal to 1 over cos x. Okay, and by definition, it is equal to 2 over exponent x plus exponent negative x. Okay, so it comes from the graph of, cos x. Okay, and it is 1 over cos x. So if we see here cos x, it is when x equal to 0, your fx is equal to 1. So for 1 over cos x, when x equal to 0, it will be 1 over 1. So we have the lines 1 here. 1. Okay, so you know that secant 0 is equal to, well, we can say that 1 over cos 0, and cos 0 equal to 1, so it is equal to 1. Next, what is the domain? Okay, so the domain is, if you see the x-axis, it can be from negative infinity to infinity. So the domain of the f is equal to whole real number. Meanwhile, the range, okay, so it is, you see the graph, the red graph is your fx is between 0 and 1, only between 0 and 1. So the range rf is y, so y equal to fx, y such that y, it is between 0 and 1, but it will not reach 0. It reach 1, but it doesn't reach 0. And if you can see that it is symmetrical about y-axis, and we have secant of negative x. So you see, since it is symmetrical about negative x, so the value of fx for the negative parts here will be equal to positive. So it is equal to secant x. Okay, but actually we can derive the value of secant x from cos x because it is 1 over cos. Next one is cosecant x. Okay, so cosecant x is equal to 1 over sin x. So it is 2 over exponent x minus exponent negative x. Okay, so here I want you to be careful. So I have alert. Okay, I will put it in red alert. Okay, so red alert. Now I cannot see the font. Okay, this 2 over exponent x minus exponent negative x is not equal to 2 over exponent x minus 2 over exponent negative x. So this is very important. Okay, very important. This is actually basic mathematics, but I have found some students did this before, so that's why I put this on red alert. Means don't do it. Okay, don't do it. This is extremely wrong. Okay, so this is the graph of 1 over sin x. You can see that it is undefined at x equal to 0. It is undefined at x equal to 0. So the domain, okay, so the domain, the f, is all value of x such that x is not equal to 0. So it is all real numbers except for 0, because you see that it is approaching 0, but it does not, it is undefined at 0. So similarly with the range, it goes to, you can see that it's going up to infinity, it's going down to infinity, but it does not, it is undefined at y equal to 0. So all value of y except y is not equal to 0. Okay, the next one is cotangent hyperbolic. So you see that we have here 1 and negative 1, since it comes from the tangent hyperbolic. So the tangent hyperbolic, you have asymptotes y equal to negative 1 and 1. So here, so for the cotangent hyperbolic, we know that cotangent hyperbolic x is equal to 1 over tangent hyperbolic x. So it is equal to exponent x plus exponent negative x over exponent x minus exponent negative x. Okay, so what is the domain? Okay, so the domain, the f, is x such that, you see, all value of x except for 0, it is undefined at 0. You can see from the graph it's undefined at 0, so x is not equal to 0. So every time you are looking for the domain, take a look at the x-axis, and the codomain come from the y-axis, okay? And the range, the range. There is a slight difference between range and codomain, okay? But in this graph of hyperbolic function, we only consider the range. Okay, so we have y such that y is in between -1 and well, we can say that y, except that y is not in between -1, -y to 1. So we can say that y such that y is greater than 1 or y is less than -1. So it does not include the value from -1 to 1. Okay,